Okay, so hi everybody. We are okay. So nice to see you again after quite a while, and this is sort of the last bit of the course now because we have this lecture and the next lecture before Thanksgiving, and then it's going to be just 1 week after that. So what this also means is that you know, we are getting into the time for course evaluations. So let me put up some of the information for that. So the course evaluations will be open for you to do online starting Monday. So let me just make sure this is okay. Okay, so you'll be able to fill them in starting Monday and going till December 13th. So you have to do it before December 13th. And the place where you access them, so there's a website, it's course-evaluations. .berkeley.edu. Okay, so you know, normally it takes you about 15 minutes in class to fill them in. So the recommendation is you take that amount of time and you know, give us some thoughtful feedback about the course. One thing that you know, so we you know, we gave out a pretty comprehensive feedback form after the first midterm, and we'll try to give you another such feedback form after the final or around the time of the final. So, but these course evaluations from HKN are also extremely important, and you know, you should take your time to fill them out well, because they'll help not only us but also whoever teaches the course next semester. You know, there's feedback here that would be very helpful. Now, there's one more thing. You know, if you run into any trouble with these evaluations, you can always email HKN at csec@hkn.mu. Okay, and there's also a 2-minute video by them, which gives out all this information. So we'll post it on Piazza, and you can look at it there. All right. Actually, while I'm talking about how we are getting closer to the end of the semester, I'm sure you already realize this because you've been working on your projects. And then just to make sure you all remember, there's a final exam for the course, and that's scheduled for December 16th from 6 to 9 p.m. Okay, so okay, so that's as far as logistics goes. Now, let me say just a little bit about where we are going to for the next. Now there are only 4 lectures left. So what are we going to do for those 4 lectures? So so today, you know, I wanted to do a little, you know, some part of the lecture, you know, getting to some of the things about coping with NP completeness that Avisha did not have time to get to last time. So I'll just do a, you know, I'll do this at a pretty high level, but you know, possibly some of this way of thinking might even help you for your project. But it's just to you know, to give you some more perspective on the subject. So we'll start with just a little bit of coping with NP completeness, since there was only one lecture for it so far. And then for the rest of the lecture today, and maybe a little bit of next time, I'll talk about an algorithm for primality testing. And I'll try to put that in perspective and say why it is that we are talking about it, what's so interesting about that. And then from there, for the rest of the next lecture, we'll talk about hashing. So we'll talk about universal hash functions and what their properties are and why these are important. And then we'll go on to talk about sketching and streaming. Maybe I should just call it streaming for now, because I'm not sure we'll do all of that. So okay, so these would be the next 3 lectures, and for the very last lecture, I'll give you a sort of a 1 lecture, quick introduction to quantum algorithms. Okay, so maybe what I should say is that for all these topics, there's going to be some part of it that you're actually responsible for, but there'll also be a large part of it which is meant for you to enjoy the ideas, to play with ideas, and just to sort of expand your horizons about what algorithms mean, right? And what this course is about, and what future courses, if you decide to go further into this subject, what they might look like. Okay, so that's sort of the, so in some sense, you should, if you're too concerned about what will be in the exam and so on, maybe this is a time to sort of take a step back and say, look, it's time to to actually enjoy this a little bit more. And if you're already enjoying the course, it's a time to do it, double down on that. So okay, so that's the thought here. All right, so so let me start with a little bit about coping with NP completeness. So so let me draw a picture of what it means for a problem to be NP complete, right? So normally, one's first encounter with NP completeness would be that once you prove that a problem is NP complete, that says it's hopeless, right? It's really hopeless to try to find an algorithm for it. Now, the fact is that the vast majority of problems, computational problems we are interested in, are NP complete. Okay, to understand how vast, you have to look at some figures, and I don't remember them exactly, but there was some figure which said, over the last whatever few years, the number of problems that have been published in journals, showing that these are NP complete, was something like a few thousand, and these were problems not, these were just problems in physics being published in physics journals about, so sort of, this number is really vast, and they show up not just in the sorts of problems that we are talking about, like satisfiability or traveling salesman, but they show up everywhere in every domain, physics, chemistry, in the natural sciences, and so it's just almost any problem you touch is NP complete. So I think there's a need to have some perspective of what NP completeness means, and to have that perspective, let me just draw you a little figure of, I'm sure you did this already, but let me just draw a picture of how I think about it. So, so let's say that you have some NP-complete problem X. Okay, so maybe TSP, some problem. Now, this is the set of all inputs, right? So every point in here is a particular input you could be giving to the problem. So maybe this input is 1 0 0 1 1 1 0. Okay, so there are whatever the inputs look like. Maybe they are binary strings, maybe they are graphs, maybe whatever they are. But these are the set of all possible inputs to this problem. So now, when we say that the problem is NP-complete, all we are guaranteeing is somewhere in here, there's some set of problems, some set of inputs, which are, where there are infinitely many of them, but we don't say how dense they are, how prominent they are. There's some set of instances, and we are saying, these are really hard, right? Okay, so when you do a reduction, when you show that this problem is NP-complete, you do a reduction from satisfiability to this problem. Well, you don't have to map your satisfiability instance to every instance here. You just map them to some instances. So all you have to do is to say, there's some instances here that are really hard, right? So NP-completeness means some really hard instances. So first, it's these ones. So the vast majority of the instances may be left out of it in a certain problem. So X could be one of these problems where, in fact, these hard problems are not everywhere. They're only in some corner here, and maybe we don't care about this corner. So what that means is if we are designing an algorithm, we have to be careful. We don't want to design an algorithm that works everywhere for every instance. But we might be able to design an algorithm that works for every instance we care about, because all it excludes is maybe these instances and a few more we don't care about. So that's completely okay with respect to NP-completeness. The other thing we can say is, well, look, if you look at an instance in here and you look at the answer, maybe the answer looks like A0 point A1, A2, A3, A sub k. Right? Maybe the answer in decimal notation or in binary notation looks like this number. And all that NP-completeness guarantees us is that there are some difficult bits in here. Maybe these are the hard bits. It doesn't tell us that the entire thing is hard. And so it could be that we can find an algorithm that not only finds, can solve these instances out here, which were not hard, even on these hard instances, maybe all that's hard is getting these low order bits. So you could get most of the answer, and that could still be something that your algorithm can find. And so this is the way, this is the picture of NP-completeness you should have. Okay, so now the question, but then when we are designing algorithms that don't work for every input, this is sort of a very different style of algorithm design than we've seen so far in the class. So how do we do it? And in the last lecture, you saw some of these algorithms, how you do them, approximation algorithms, which sort of leave off these least significant bits of the answer, or maybe other heuristics which sort of try to work in some of this domain. So I wanted to say a few more words about it, to say, look, many times these heuristics are designed through some sort of intuition, and the kinds of intuition that you might have, that lead to these algorithm design. So to design heuristics, these heuristics might be based on intuition that comes from either geometry, or from nature, right? or from nature in terms of maybe through physical systems or through biologically inspired heuristics. And so let me give you a few examples and of these, and I'll try to do them at a very sketchy level, so it's not but like I said, some of this maybe kind of thinking might be helpful for your project, or it might just be something that you enjoy and it's meant to broaden your mind. So that's what this is all meant for. Okay, so let me so what I want to start with is a problem which is called graph partitioning. So in this graph, in this graph partitioning problem, your input is some graph. So you're given this graph with number of vertices, edges, whatever that looks like. And what's your goal? So your goal is to divide the vertex set into two parts. So you want to divide the vertex set, so you want to divide it into V1 and V2. So you want them to be disjoint, and you want each piece to be between 1/3 and 2/3 of the entire vertex set. Right, so you want it to be roughly 50-50, but we are willing to accept anywhere between 1/3 and 2/3. Okay. And you want to minimize the number of crossing edges. So you want to find a small bottleneck in the graph, right? And of course, one way you could say, well, I want to minimize the number of vertices, edges cut, is I could just say, well, let me pull out one vertex, but that's not okay, right? Because we want something where you pull off a good chunk of the graph, So this is an NP-hard problem. It's an NP-complete problem.
Maybe it's worth mentioning that if you don't have this condition on the size, and this is just min cut.
Yeah.
Min cut we know how to solve.
Exactly. So the point here is that we are insisting that the cut should be, should be roughly equal on the two sides. Now, it turns out that there's another condition we can also try to do, which is what's called a normalized cut. Which is, you find V1 subset of V such that okay, so you find a cut. So let me just say it's V1, V2. So you find V1, V2 such that what you're trying to minimize is the number of edges that cross from V1 to V2 divided by the minimum of V1, V2. Okay, so what is this saying? So let me just try, so let me say that V1 is a smaller side. So what are we trying to do? What we are trying to do is we say, look, now we no longer require that you choose at least 1/3 of the vertices on each side. Now we are okay with your choosing a small number, small set V1. V2 can be pretty large. But now what we want is that the number of edges that cross from V1 to V2 should be sort of small proportional to the size of V1. So it's more normalized. If you have a tiny cut, a really tiny cut which involves only 1% of the vertices, that's fine. That's good enough for us. And of course, if you wanted to solve this 1/3, 2/3 problem, you could just keep solving normalized cuts, and you would, you could keep picking up these normalized cuts until you get to at least 1/3, and then you're good. Okay, so that's the problem that we're interested in. So now, how do you solve this problem? So one way to solve this problem is to map it into geometry. So here's one way that you might imagine doing it. Well, what we could do is we could sort of map all these points onto the unit disk. Yeah. So and we'll map all the vertices onto the unit disk in R2, in the two-dimensional plane. And what we want to do is we want to map, we don't want all the vertices to sit on top of each other. So we map them so that on average, every pair of vertices is the distance between them is at least 1, let's say. But what we want to do is we want to think of the edges as being represented by springs. So there are springs that are trying to make, if there's an edge between two vertices, then we want that edge to be as small as possible. So we are sort of mapping all the vertices, onto the unit disk in such a way that we think of the edges as these little springs, and somehow, but on the other hand, we also have some forces between these vertices which repel them. You think of them as magnets which are repelling each other, so that the distance between these vertices on average is pretty large. So now we have, now the geometry reflects the graph structure. And so if you want to divide up the graph into two pieces, all we have to do is find a good cut of this surface of this unit disk. And in fact, it turns out once you do such an embedding, you can just cut this disk at random and you'll get a good cut in the graph. How good? Well, good in this sense, right? So, I mean, there are going to be graphs where you won't do that well, but you'll on every graph you'll do well in this sense of, maybe the least significant bits are going to be very hard, but you'll be able to do something with the most significant bits. And so it turns out that the space in which you do this embedding matters a great deal. So it matters whether you were doing this embedding in the two-dimensional plane, or if you do this embedding on a line. If you do the embedding on a line, and if instead of, when I say that points are close, for an edge, a point, we want to minimize the sum of the distances between, so we want to minimize the sum over UV in the edge of the distance between UV. Okay, so we want to put our vertices down. Okay, so in such a way that edges tend to be short, right? But on average, these vertices are spread out quite a bit. So the average pair is distance 1 from each other. So this is sort of, this is the sort of embedding we'd like. It turns out that there are these algorithms called spectral algorithms, where you find the eigenvectors of the adjacency matrix of the graph. And what they do is they do this embedding where they minimize the sum of the squares of the distances between pairs of vertices that are joined by an edge. And that gives you a certain kind of cut. So if you do that, and if you take a random cut, you get a cut with a certain property. it turns out that there are even more sophisticated algorithms where instead of doing this embedding on the real line or in the two-dimensional plane, you do the embedding in n-dimensional Euclidean space. So you're embedding all these points in a unit ball in an n-dimensional Euclidean space. And then that's something that you can do efficiently, and that gives you even better results. Okay, so this is the way in which geometry enters into these solutions. So now, how would you approach these kinds of algorithms? Well, you could either study all these algorithms, or you could use the fact that people have actually written lots of code for these, based on these particular algorithms, the spectral, and these are called semi-definite programming. And then there are lots of techniques that have gone into it, from these algorithms that were designed, by many of us. Then there are many other techniques that went into it before it got into these heuristics that you can actually use. And so you can actually find these online. But now, if you were doing some they involve not just doing a cut where you cut the graph into two pieces, but you might want to cut it into multiple pieces. Okay, but now let's say that you wanted to use one of these for your project. Well, you have to take the problem that you're actually given in your project, and you would have to map it onto whatever problem it is that this solver is solving. And while doing that, you have to sort of, you have to be a little careful that you know that the solver is not going to be solving all these problems, because there are some really hard problems. And it's not going to be giving you all the bits, it's going to be giving you some of the bits of the answer. So you had better make sure that whatever you are interested in gets mapped into the kinds of instances that the solver can solve, and maybe the kinds of precision, to the kind of precision that the solver can actually help you with. So, there's a lot of, some of these things you can actually understand analytically, and some of these you just have to guess or have a feel for. And that's something that you have to think about. Okay, so maybe what I'll do here is I'll stop for a minute for questions, and then I'll say talk about a couple of other things.
Could you quickly go back over how you constructed the embedding in the unit disk?
I didn't, for the unit disk, I just said, suppose, so here I was just saying, for the unit disk, I was just saying, suppose you could minimize over all edges in the graph of the distance between u and v in some either Euclidean distance or the square of the Euclidean distance, while making sure that the sum minimize the sum over all uv, while making sure that the sum over all uv, now not in the not edges, the distance between u and v is divided by, is say n choose 2, something like that, because now this is saying if you look at all pairs of vertices, there are n choose 2 of them, and if you look at the sum of the distances, it's n choose, so the average distance is 1 between any pair of vertices, not necessarily connected by net. So I was saying, suppose you could come up with such an embedding, then you would, just, your graph has now been somehow represented in this geometry, and now you need to cut the geometry into two pieces, and that's easier.
Oh, gotcha.
Okay, now I don't know how hard it is to do this in 2 dimensions. In 1 dimension, that corresponds to spectral methods, and that we know how to do. In n dimensions, this corresponds to semi-definite programming that we know how to do. I think in 2 dimensions we could also probably do it, but in 1 dimension and in n dimensions, these are very useful sort of algorithms to have, and they give us
Isn't a good heuristic to embed graphs in planes to look at like top eigenvectors?
Yeah, exactly. So
I don't know how, like if it's rigorous or not, but it works in practice very well.
right. Yeah. So more questions?
People can feel free to raise their hands. But no on my end.
Okay. It would be good to get a sense of how, whether people, quickly in the chat, whether people find this useful, because then based on that I'll either say very little or more about the couple of other things I wanted to talk about. So I can either skim over them very quickly or depending upon how interesting people find them. Any feedback?
People could drop their opinions in the chat. Okay, we have one person says it's interesting. 2 people say it's interesting. Others say no. Okay, seems pretty split.
Okay. Okay. So let me just say relatively.
One thing that I didn't talk about is the usefulness of LP in solving NP-complete problems.
Of integer linear programmings.
Yeah.
Okay.
Or just
okay. So let me just say a couple of things then. One is okay. So one is of course you can formulate a lot of you can formulate any NP-complete problem as an integer linear program. So what it means is, we know that linear programming is efficiently solvable. It's, we have heuristics like the simplex method. There are actually polynomial time methods, interior point methods, and so on. And these are extremely well programmed. But now, if you insist that the solutions are not just real numbers, but they're actually integers, then the problem becomes NP hard. And okay, so the fact that integer programming is NP hard means that whatever problem you are interested in, you can reduce it to integer linear programming. But the point is that there are very good heuristics for integer linear programming, and you can find these available to you. And it's sort of at a high level, it should be clear that there ought to be a heuristic, because what you could do is you could relax the integrality constraint, and you could just say, give me any solution, right, with real numbers. And then once you get that solution, you could round the real numbers to, so you could just solve the LP and then do rounding. And now, if you do that, well, once you do the rounding, your solution might not be as good. But there's a second problem that might happen, which is your solution may no longer be feasible, right? You're supposed to satisfy also these constraints, and maybe those constraints are no longer met once you round. And so now you have to use some heuristics to make sure that your rounding doesn't make you infeasible. But you can imagine that this can all be done. And so, well, again, if you want to use these integer linear programs, what you want to do is you want to do a reduction in such a way that you map the problem that you want into a very natural integer linear program, so that it's not too complicated, and that the ILP solver actually does well on it. So that's one more technique. There's one final technique that maybe I'll mention, which is or possibly which is simulated annealing. Which is motivated by physical intuition now. So the way it's motivated is as follows. So you look at all possible solutions to your problem. So for example, if it's satisfiability, then all possible assignments to the formula that you're interested in. Okay, so you look at all potential solutions. And so for potential solution X, there's a cost, C of X, right? This is how, and let's say that you're trying to minimize C of X. And so if this potential solution X was a TSP tour, then C of X would be the length of this tour, and you're trying to minimize C of X. So, what you do in simulated annealing is you now associate a temperature. You think of these solutions as configurations of a physical system. You think of it as a thermodynamic system. So these are so you associate a temperature T associated with this system. So behind the scenes, we have this picture. Here's X. Here's the cost of X. And maybe the cost of X is some profile like that. And what we are thinking is, if you do local search, you start from somewhere, and then you do hill climbing, you descend, and you descend into a minimum, and you get stuck. And so what we want to do is what a physical system would do. And the way you find, so in a physical system, these X are configurations of the system, and C of X would correspond to this corresponds to the energy of that configuration. So X corresponds to a configuration, C of X corresponds to the energy, and the system itself is trying to find the lowest energy configuration, right? That's what it tends to relax into. But often, in order to make interesting physical systems relax into their lowest energy configuration, what you do is you start them off at a high temperature, and then you gradually cool down the temperature until it relaxes into its lowest energy state. And so the idea is, the physical intuition is that at high temperature, the system really cannot tell what the energy of any, it's so excited, it doesn't even, whether its current configuration is high energy or low energy, it can't even tell, because it's just bouncing around all over the place. But then as you lower the temperature, it has less energy, so it bounces, but not so much. So if you start from here, initially, and you're at a high temperature, well, you're just bouncing around. But as you lower the temperature, you're bouncing around somewhat, but even if you're at some temperature and you're bouncing around, you still notice that the energy is getting lower here. But if you're at a suitably moderate temperature, even though out here you're at a low point, you're at a local minimum, you'll bounce around, and the chances are that you'll bounce around and get out of this local minimum and find your way sort of further into this lower, more global minimum. So in simulated annealing, you start at a high temperature. So start with T high, maybe even infinity, and then you gradually lower the temperature up to the point where you're close to T equal to 0. Okay, and in the meantime, what you're doing is you have some. Okay, so now what you want is you want to have some algorithm which at each such temperature sort of, when you start at high temperature, it's sort of, the steady state distribution is uniform on all possible solutions. And at any given T, you are in what's called the Gibbs distribution, which is what the physical system would be at that temperature if it was in complete equilibrium. And in the Gibbs distribution, the probability of the configuration X is proportional to e to the minus energy, which would be C of X, divided by temperature. Right? So when the temperature is infinity, C of X doesn't matter, and every configuration X is equally likely. And now what you do is, as you drop the temperature when T is close to 0, then the only configuration with non-zero probability would be the lowest energy configuration. And so now how do you actually do this? Well, you look at all your solutions and you create a graph on all possible solutions. So these are all possible solutions. You create a graph on them where if this is solution X, that's a solution X prime, and X differ only in one coordinate, right? So for example, they differ in 1 or maybe 2 coordinates. So you can move locally from one solution to another, and you put in an edge. And so you're walking, what you're doing is you're walking on this graph. This is X and X prime are adjacent if differ in 1 coordinate or in 2 coordinates, and the way you get to this distribution is what you do is, at high temperature you just pick X at random, and now you start lowering the temperature, and if you're currently here, you pick a random neighbor, and if you're going from X prime, you pick a random neighbor X, and you see if E of X prime is greater than E of X, meaning then you always move to X. If E of X prime is less than E of X, meaning to move from X prime to X, you're going to be moving to a higher energy configuration. Then you say, well, I'm actually not that happy about moving to a high energy configuration, but I'll do so if the temperature is high enough. So you move to X with probability e to the minus delta over T, where delta is E of X minus E of X prime. Okay, so you look at how much higher the energy is of the new configuration from the one that you are at, right? The new solution from the one that you're at. And you say, look, I'm willing to go to a high energy configuration, but only with low probability, depending upon the temperature. So if the temperature is high, I don't mind going up a lot. But if it's low, then I want to stay pretty much either go downhill or go uphill just a little bit. So this parameter T sort of tunes that value. Okay. There's a lot more one can say about why these heuristics might do well and how to even speed them up further. So if you want to look it up, there are ways to speed up simulated annealing with what's called a go with the winner's heuristic. Okay. Which itself, interestingly, you can think of as being somewhat inspired by, evolution and you know, survival of the fittest. So you know, that those are some of the ideas that you might think about if you're trying to think of heuristics in these cases. Okay, so let me stop here, see if there are any more questions, and then I'll move on to primality testing.
Can you say a little bit more? What does it mean, go with the winners heuristic?
Oh, okay. So what is go with the winners? All right. So, so the heuristic is this. Let's say, you know, one way you can think about solving an optimization problem is you're actually searching in some space, right? And think of you know, think of it if there are people who are searching for something. Now, you know, and let's say that you had not one person, but you had many people who are searching for something, right? In some space. So your space is some sort of a graph. You know, there's some sort of graph, and then there are these people who are all searching for something which is the solution you're looking for. So now there are two ways you might want to organize this search. You know, one way is you just tell everybody, look, we are searching for the best you can find. So, you know, all of you go out there and you do your search individually, right? And that's going to, you know, that's going to give you some performance. But, you know, many times it's actually helpful to coordinate these different these people searching. And so one way you could do the coordination is by saying, look, let me let me coordinate you completely. And that may not be such a good thing, you know, to have everybody sort of do things that are pre-organized. So there's an intermediate thing which turns out to be a very helpful thing to do, where you say to these people, look, just behave independently for a little while. And then once you do this for a certain amount of time, then you can call out and say, you know, those of you who are doing well, you know, yell out that you're doing well. And those of you who are really badly stuck, you know, say that you're badly stuck. And then we'll take the people who are badly stuck and we'll teleport them to the ones that who are doing well. Okay, so maybe, you know, maybe these guys were searching in different places, and this one seems to be doing really well. That guy is very stuck. This one is very stuck. That one is doing moderately well. Okay, so we now move this person over here, this person maybe over here, and now we say, well, we have two searchers here and two here. And now we again let them, we don't say, well, this person did pretty well, so you follow that person around. No, we say, look, that was in the past. Now you just search independently for a little while. And so you see where you get to, and then again you say which ones are doing well, which ones are doing poorly, and you move to the ones who are doing well. And if you do this, there are many situations where you can do exponentially better than either coordinating completely or not coordinating at all. If you do this sort of thing where every so often you say, who's the winner, and let's go with them. The reason this is like evolution or survival of the fittest is, another way you could do this is you could just say, look, everybody who does poorly, you know, depending upon how well you're doing, you get that many more copies of yourself. And if you're doing badly, you die out. So instead of keeping the total number of searches constant, you just have you know, searches which reproduce or they die out. And then if you know, this is more like nature and evolution. And then this turns out to be a really good heuristic. Now, okay, so I can say one more thing about this, and then I'll stop. So it turns out that this is, you know, this is actually quite related to simulated annealing. And the reason it's related to simulated annealing is because, you know, think about this large, in simulated annealing, there was this, you know, this set of all possible solutions. These were all solutions, right? And we were we were searching among them, and we started with at a high temperature where everything was equally likely. But then, and we could move from solution to other nearby solutions through these edges. Now, what happens as you lower the temperature is some of these edges become very hard to actually traverse because the energies go high. So what happens is, this graph gets split into two parts where you really cannot cross from one side. You can cross, but it's so unlikely that you'll cross from one side to another. And then you reduce the temperature further, and maybe it gets split up into more pieces like this, right? So if you think about it, what happened is you started with one vertex, and at the next step, it got split into two pieces like that. And at the next step, this got split into three pieces, and that got split into three pieces, and so on. So in simulated annealing, what you're doing is you're actually trying, you're walking down a tree implicitly. And one way you can arrange this is that, you get stuck if it turns out that one way to think about what you're trying to do is you're trying to walk down this tree, and, at each step, simulated annealing tells you, with what probability you got stuck in the left half or the right half. So it gives you a probability P, 1 minus P of going left and right. And here there'll be a probability Q1, Q2, Q3 of going in these three branches and so on. That's what simulated annealing gave us, right? And now you can either, and it turns out you can set it up so that a good solution is a way of traversing this tree where you go down to a deep leaf in this tree. So now, of course, we don't see this tree. This tree is something that if we could understand the problem completely, we'd see the tree, but we have no idea that, what this tree even looks like. But one way we could run simulated annealing is we run it and we see how good a solution we found, and then run it again and see how good a solution we found, and we just repeat 100 times or 1,000 times and take the best solution, right? That would be like doing this search with 1,000 people, but you don't coordinate them in any way. So the other way you could run simulated annealing is you just run 1,000 copies of simulated annealing simultaneously, and then you're walking along, each of your copies is, and then you sort of heuristically decide which ones are doing well, which ones are doing badly. And then you take the copies that are doing badly and move them over to the ones that are doing well. And then you keep going. And it turns out that for many structures of trees like this, so this go with the winners does, at least as well, but it can sometimes be exponentially faster than just repeating many times. So that's the go with the winners here.
We have a question. Is this like a Monte Carlo search of the tree from Rashab?
It is Monte Carlo, yeah, because right to begin with, this tree was sort of in our minds. What was happening behind the scenes was we are actually running simulated annealing on this large set of solutions, right? And simulated annealing is inherently Monte Carlo because what you're doing is, you go from the current solution to a neighboring solution, and if the neighbor is better than the one you're at, you always go there. If the neighbor is worse than you, then you go there with some probability. So in that sense, it's Monte Carlo, right?
You also pick the neighbor randomly, I guess.
You also pick the neighbor randomly. Yes, that's right. Okay.
We have one more question from the chat. I'm not sure I understand it. Is go with the flow similar to particle filtering, where our resampling distribution is a function of the particles C of X cost function?
Sorry, it's a okay. So first of all, it's called go with the winners.
With the winners.
You're sort of taking, you're sort of seeing who's doing well, and then you're joining them, right? Is it similar to particle filtering? I'm not sure. I'm not sure what particle filtering is, but
I'm not sure either.
yeah. So it could be. I mean, it might be similar, but I'm not sure.
There's one question from Piazza. How do we know what C of X is for each problem, and what represents an energy state, and how do we determine energy states for our project, for example?
So the C of X is an analogy to the energy, right? So what are we actually looking at? So let's say what's a nice problem that was covered recently? Was it traveling salesman problem or something?
You can say even for SAT, right? For SAT, it's not really clear how to define energy. You need to think. I mean, you need to do something, right? So
yeah, okay. So let's see how we do it for SAT, right? So you're given some SAT formula F of x1 through xn, and let's say it's a you're given a bunch of clauses C1 and C2 and C sub m. Each of these clauses, if it's 3 SAT, each of these clauses has 3 literals in it. So now you look at a particular assignment x is x1, x2 up to xn, and you say, how many clauses does it satisfy? So you look at number of maybe we should look at number of unsatisfied clauses.
mm-hmm.
Right? So the solution we are looking for has 0 unsatisfied clauses. So that's the lowest energy configuration. But now maybe we picked an assignment which satisfies half the clauses, but m over 2 of the clauses are not satisfied. So then we'll say its energy is m over 2. Maybe we have some other assignment which satisfies all but 5 clauses. So its energy is 5 because everything else is satisfied, but these 5 clauses are not, right? So now what we are looking for is either the lowest energy configuration, one that satisfies everything, or something that satisfies almost everything, right? So C of X is something that we can tell from the problem that we are looking at. This is the thing that we are trying to optimize, right? And now what we do is we say, look, even though this is actually a combinatorial problem, it's a computational problem, we'll draw an analogy with a physical system. So we think of these, each of these configurations as a configuration of our, of some physical system. And then if the physical system happens to be in configuration X, then its energy is C of X. That's what we had, that's our analogy. And then we think to ourselves, how would this physical system behave? Well, what it does is it locally changes itself. So now we move from one assignment to another. And how do we move? Well, we change one of the variables from 0 to 1 or 1 to 0, right? So we move from this assignment to a neighboring assignment. And then we say, what would this physical system, physical systems change locally, but what happens, well, so it turns out that a good dynamics for this system is to say, well, if then you pick the neighbor at random, and if it's lower energy, then you just move there. If it's higher energy, then you move there with some reluctance. And what's a measure of your reluctance? It's the temperature of the system. So that completes our analogy with this physical system, and that's where this rule comes in. That we had, which said, which said you move with probability e to the minus delta over t, where delta is the increase in energy.
There's one more question from the chat. I'm not sure if we got it yet, but I don't know if he wanted to move on or not.
That's okay. We can take it.
I hope I'm not repeating anything. So Selena is asking, would our desired probability distribution be the one where most of the probability is in the global minimum?
Yes, that's the desired probability distribution. Now, when you actually run, so okay, let me tell you the hope behind simulated annealing. The hope is that, when we start at the high temperature, of course, we know that we should be in a uniform distribution of overall solutions, and we'll assume that it's easy to pick a random assignment, right? You just pick every variable to be 0 or 1, true or false with equal probability. So that's easy. Now we start reducing the temperature. What we'd like to happen as we reduce the temperature is that we should be at the equilibrium distribution for that temperature. And it's a short calculation. You have to know a little bit, but it's not very hard to show that the equilibrium distribution would be this Gibbs distribution, where the probability that you're in assignment X would be e to the minus c of x over t, right? So that's our desire. And what's true is that if we use this rule that we wrote down here, that we move with probability e to the minus delta over t, if we repeat that for an infinite amount of time, then we'll certainly get to this equilibrium distribution. The question is, will we get there quickly? That's our hope. Our hope is that we'll get there quickly. And then what we'll do is we'll keep reducing the temperature. And as we keep reducing the temperature, this equilibrium distribution, the Gibbs distribution, starts focusing more and more on the lowest energy configurations, which means, if we get the temperature down to 0 or very close to 0, then it'll be focused exactly on the lowest energy configurations, which means that if you now look where you are, you've found the best solution to your problem, right? The optimal solution. Now, of course, in practice, that won't happen, right? Because this might be an NP-complete problem, which means that it shouldn't be solvable in polynomial time. And so what would happen is, as you lower the temperature, you will not go into the Gibbs distribution. You will get stuck somewhere locally, right? And so that's the problem. So we are hoping that we'll get there, and it's a heuristic. We hope that it'll do it. And there are certain problems where it does extremely well. There are other problems where it doesn't do well at all. And there are problems where, it does much better if you do this sort of, you apply more heuristics to it, like go with the winners and others.
Some people are asking about how to schedule the temperature. I mean, I answered that it's a heuristic, but maybe there are some better answers for that.
I think that, these are difficult questions, right? Because, there's also the question, should you just be lowering the temperature monotonically, or should you actually, that's annealing where you just cool quickly, or you should do tempering where you cool it and then you heat it up a little bit and then cool it again, right? So that, maybe you made your way through some local optima, and then now you want to heat it up again to get out of some local optimum and go further. And so these are all, I think that there's a lot of, I don't really know, I'd have to think about it a lot, but there are people who think about these things. I don't. Anything else?
I think that's it.
Okay, great. So let me try to, okay, so there's not that much time left, which may be let's try to make it a feature rather than a bug. So the next thing I want to talk about is primality testing. And, you know, there are two motivations to talk about primality testing. One, okay, actually, maybe I should say there are many motivations for talking about primality testing. Okay, so the first thing is that it's a very beautiful example of a randomized algorithm. Okay, so the problem is easy to stay. You're given as input n, and you're asking is n prime. Okay, so it's there's nothing randomized about the question, but this is a question for which, for the longest time, the only efficient algorithm known was a randomized algorithm or probabilistic algorithm. And where it flipped coins, and it didn't tell you for sure whether this was a prime or not, but it gave you the answer with very high probability of success. So, and even now, when there's a deterministic algorithm known, it's much slower than the randomized algorithm. So the one that's used in practice is the randomized algorithm. There's a second reason, which is going to come up very soon in what we're going to be doing after this, which is primes and their properties show up in hashing. So as well as this sort of probabilistic thinking shows up in both hashing and in streaming algorithms. So it's a good thing to know about it. Anyway, it's a good segue into that field. And then there's a third good reason to think about it, which is, of course, primality testing sits right at the, it's at the center of cryptography. And when you think about cryptography, cryptography itself sits at the intersection of algorithms and complexity, right? So in other words, both of these things that we've been talking about in this course come together in cryptography, because what you want is problems which, okay, so you want to, so cryptography sort of sits in this intersection between algorithms and complexity. So what do I mean by that? You want some problems which are easy, so they are good algorithms, and then you want something very close to them, to the same problems, which are very hard. Like what we said with NP completeness, but maybe in some ways even harder. And the ways in which we want the problems to be harder is that we don't want them just to be hard in some small place, but we want them to be uniformly hard all over. And we want them to be hard not just in the least significant bits, but we want them to be truly hard everywhere, right? That's what we want from cryptography. So we want this juxtaposition between problems which are very easy and some very closely related problems which are very, very hard. And we want these to be sitting right next to each other. And so primality testing is one of these kinds of problems, where it's set, the thing about it is it sits right next door to another problem which seems very hard. And so this hard problem is factoring. Right? So what we want to say is that primality sits here and factoring sits there. And they are sort of sitting very close to each other. They are, if you don't look closely, you might think they're the same problem. So what's factoring? Well, factoring is the problem where you're given n, and you can pose it in one of two ways. You can say, well, give me the prime factorization of n, or you can just say, is n equal to n1 times n2? Okay, no, not is. factoring is you're given as input n, and you're told write n as n1 times n2. Okay, so in other words, you're given input n, output any n1, n2 such that n1 times n2 equal to n. You know, and or say not possible. So in factoring, you're being asked either split the number into two parts, or tell me that it's impossible. Right. So you know, if you were given a number like such as 35, then you say, okay, this is 5 times 7, right? Or if you were given a number like 29, you'd say, well, actually, sorry, I can't split it. It looks to me like it's a prime. Okay, so the reason that these two problems look almost the same is because, you know, initially you think about it and you say, look, I don't understand. You know, you want me to tell whether n is a prime without, you know, surely the way to do it is I'll try to factor n, and if I don't succeed, then it's a prime, and that's how I do it. So give me a break. You know, why should these two problems be so different? And it turns out that one of these is a really easy problem and the other is a hard problem. Right? It's a really hard problem. It's so hard that we base our cryptography on it. And then we can further say, well, it's so hard that we can base our cryptography on it unless we have access to a quantum computer, in which case it's easy. And then, okay, so that's what makes this, you know, makes it even more interesting than it used to be. Right? Okay, so now, so how does this test for primality work? So the way it works is, instead of trying to factor n, you come up with some sort of a, you know, if you draw an analogy, then what we want to do is more like a litmus test, right? We want to, you know, we are given, you know, imagine we are given an acid or a base and we are trying to tell which it is, and you use a litmus paper, and you look at the color it turns, and you say, well, this is an acid, or it's a base, and you do it without identifying which acid or which base, right? So the claim is that telling whether n is a prime is much simpler than trying to actually figure out, if it's not a prime, how to factor it. And the way that works is something that, you know, I mean, the beginning of it is something that you saw in CS170, which is Fermat's little theorem. Which says, if n is a prime, then for all a not congruent to 0 mod n, a to the n minus 1 is 1 mod n. Right? So this seems very much like a litmus test, right? It says, if n is a prime and you subject it to this, then the thing turns into 1, right? And so you could you know, to test whether n is a prime, you could just pick a number a, raise it to the n minus 1, and if you get anything other than 1, you can say, well, it's definitely not a prime. The question is, if it does give you 1, what do you do then? Right? And it turns out that if we pick, you know, if we pick a over and over again, and it keeps coming up 1 mod n, then we are very close in a very formal sense to being able to say, yes, n must be a prime. Right? And so exactly under what circumstances and why we should be able to say that, we'll look at next time. But the algorithm, it just follows from you know, it turns out you have to do a little more work to say it, but then we would end up saying, this is our litmus test, and it involves just picking a at random, raising it to the n minus first power, seeing whether it's 1 mod n, and if it is, we can stop right there. Or we repeat this a few times, and that would be good enough for us. Now, actually, I should say one other thing. You know, there was, you know, there are people who work on these things. They devote their lives to it. One of the people who did, wrote in a paper that, you know, if you pick a equal to, if you try 3 numbers a, you know, 2, 3, and 5, and you get 1 mod n each time. You know, take 2 to the n minus 1, you get 1 mod n, 3 to the, you know, and so on. And if n was picked at random and it satisfied all 3, then you can sort of say it's an industrial grade prime. You know, it's good enough for the purposes of, you know, the chance that a randomly picked n, which fails, you know, which passes the test for a equal to 2, 3, and 5, that it would not turn out to be a prime is so small that you don't need to worry about it for industrial purposes. And the industrial purposes mean for cryptographic purposes. Right, so, okay, so that's where I'll stop, and then we'll pick up next time. I'll just stop for questions.
To check for 2, 3, and 5 on the like easier ways.
I'm sorry?
So to check for coprimality with 2, 3, and 5 on the like easier ways, like looking at the last digit.
No. The claim was, okay, so if you check, so for industrial grade, you know, this was sort of tongue in cheek. They said test is 2 to the n minus 1 congruent to 1 mod, and test 3 to the n minus 1 congruent to 1 mod n, and 5 to the n minus 1 congruent to 1 mod n. And if all these 3 hold, then, you know, then I think this was Carl Pomerantz, you know, he was in his paper, he said, well, you know, you could call these numbers, you know, if you picked n at random and, you know, maybe you picked n to be a, I don't know, 2000 digit number picked at random, and you did these 3 tests on it, then this should be enough for you to be pretty confident that n must be a prime.
Well, like for these numbers specifically, we could like look at the last digit to see if it is coprime, say with 2. Why do we need the Fermat's theorem?
You're not checking whether it's coprime with 2. You're saying it must be a prime number, meaning it's not divisible by anything other than 1 and n. It's a honest to goodness prime. That's you know, that's what the assertion is. That.
Okay.
Now let me say one other thing. there's something a little bit, there's something that you have to be very careful about here. The number n, so n may be a 1,000, maybe 1,000-bit number, which means n is about 2 to the 1,000, meaning it's not just an astronomical number, it's sort of beyond an astronomical number, right? There are not n particles in the universe. But the amount of time that we want to take to determine whether it's a prime or not is determined by the number of bits, which is only 1,000. The length of the number to write it down is only 1,000 bits. So little n is 1,000. It's the length. Okay, and the time that we want to spend in an algorithm is polynomial in little n. Right, so we are willing to take 1,000 steps. We're willing to take 1,000 squared steps or 1,000,000 steps, but we are not willing to take 2 to the 1,000 steps, which is what n is. So the number itself is truly beyond imagination. But when we write it out, it's only 1,000 bits. And that's what we do in cryptography. So we want to find a prime number which is that long. So we are given a 1,000-bit number and we want to know, is it divisible by anything other than itself and 1? Right? That's the challenge that we are facing. And the way to face it is by saying, take this number and run this test on it. So pick an A at random, raise it to the n-1. Now, raising it to the n-1, okay, now you should be really worried because we are raising A to the power what? Well, to the power n or n-1, but n is this astronomical number. So how could we possibly do this, right? I mean, surely if you were going to multiply A times A times A times A, they aren't, they aren't, I mean, n is larger than the number of particles in the universe. It's larger than the age of the universe in femtoseconds, meaning if you could multiply A by itself in the smallest fraction of a second you can think of, it would still take you more than the age of the universe to multiply A by itself n times. So, so there's something to think about in terms of how do we even do this multiplication and check whether A to the n-1 is 1 mod n, right? So we had better come up with an efficient algorithm for that, where efficient means it runs in time proportional to 1,000 or 1,000 squared or 1,000 cubed, right? That would be okay. And then there's the other question, how do we know that this test is good enough? We know it from Fermat's little theorem that if n is a prime, it'll pass it. But how do we have any guarantee that if n is not a prime, that it'll fail it, so that we can actually distinguish between primes and not primes? So how do we know that that happens? And then, if you remember, the proof of Fermat's little theorem, this was possibly one of the most beautiful proofs you saw in CS170, right? So if you have any nostalgia for that, and if you wanted to look up one proof, this is one of the nicest proofs you ever saw in CS170. Okay, so any other questions?
Can I ask how quantum computers can do it like so easily? Like just brief idea.
So, okay, well, I'll try to give you a brief idea in the last lecture of the semester. And that's December 3rd. But is there another way of, the quantum world is really strange. I mean, there's a certain sense in which Okay, so what's a computer? You know, a computer is a nicely packaged physics experiment, right? Because, you know, behind the scenes, you have these currents and voltages and so on, and you have, you know, you have these rules according to which you can add or subtract or do Boolean operations, right? So, but who's carrying out these Boolean operations? Well, it's nature that's carrying them out, right? So essentially, your computer is a very nicely packaged physics experiment. It's not an experiment because we understand what it's supposed to do, right? So that's the difference between a computer and an experiment, right? You already understand how it should behave, and then you piggyback on nature, and you say, would you please do this for me? You know, every time you do a computation, you are sort of making this request to nature, would you please solve this for me? And it does, you know, it does what it does, and it gives you back the result. So it turns out that, you know, at the quantum level, nature just works in ways that we wouldn't even begin to imagine if we were, you know, just aware of interaction with the world that we know, you know, the classical world. And so it turns out that in the quantum world, one, you know, while we are not looking, you know, as long as we are not looking at a quantum system, then it goes off and it does completely crazy things. And these crazy things it does requires a huge amount of work. So, you know, behind the scenes, while we are not looking, nature goes crazy and does an exponential amount of work. But then as soon as we look at that experiment, as soon as we look at the outcome, it sort of very quickly pretends nothing was going on. You know, all that exponential stuff that was going on behind the scenes sort of disappears, and you just get left with a small, you know, n-bit string that's given to you, which sort of says, which is some summary of what happened behind the scenes. And so the quantum factoring algorithm is a way of using that summary that's left behind by this crazy stuff that nature is doing while nobody's watching, and extracting some, you know, getting nature to, you know, of making sure that this summary includes somewhere in the answers to the factoring problem. And so, you know, in the last lecture, I'll give you, you know, I'll try to show you how that actually happens.